Algebra 2, we are going to continue on with functions, but this time with one-to-one functions. So we already know, I guess, what it means to be a function where the x values do not repeat. And what we're going to get at now is that the y values cannot repeat. For each one x value, there's exactly one y value. And we're going to show that by talking about these two separate functions. So they're both functions, no x values repeat. Now the difference between f is if you plug in -2 in for the x coordinate into the domain, 2 times -2 is -4. Plug in 0 for x. Okay, so 2 times 0 is 0. Plug in 2 for x, and this mapping diagram would show that we have exactly one y value for each x value. The difference, though, with this one, I'm actually going to start with 0, and there's a reason for that, because 0 squared is 0, and 2 squared, when I plug that in, I get 4. But the thing is, when you're writing a mapping diagram, you don't want two numbers that are the same over here. And if you put -2 in for x and you square it, just a reminder, scratch work, that means -2 times -2, and a negative times a negative gives you positive 4. So we are mapping and we're getting y values to repeat. So that's the moral of this, is if a function is one-to-one, so in order to be a function, x's cannot repeat. So that shouldn't be an issue. I don't think I need to write that down, but you might want to. But also y's, the y values, cannot repeat. So we can look a little bit more into that as we do this. I guess I could have written that right here. What is fundamentally different between these two functions? One had a different y value for each x value, whereas the other, the one that was not one-to-one, had the same y value happen. And that's exactly what this statement is. I know it's a lot complicated because it has these not equal to's. So the very lame explanation is what he put in parentheses. So if you wanted to read a math textbook, the top sentence would be in the math textbook. In my class, though, you would hear me say this: different inputs give different outputs. X's cannot repeat and Y's cannot repeat. So as we look at this, only one of these tables represents a one-to-one function, and it just shakes out to, okay, so this first one, this isn't even a function. So I'm just going to write that out. Not a function. I probably shouldn't be circling this because I'm going to circle the correct answer. But I'm pointing out where we have issues. Well, we have y's repeat. This one is a function. We have all the different x's, but it's definitely not one-to-one. By the way, sometimes I spell out the word one-to-one because if I write it in the notation, some students say, well, that kind of looks like the absolute value of a negative. But that is acceptable if you want to write it that way as well. But usually I write it out, 1-2-1 spelled out. Okay, I don't know what else to say except number 3 is what we want. That's perfect. All the x's are different. All the y's are different. And then what's our issue with number 4? Option 4 is actually both. It's not even a function, nor is it one-to-one. A couple issues there. As we move on, we can talk a little bit more about what makes a function. Well, right now we're just talking about relationships. And the very first question is to circle the two graphs above that are functions. And what needs to happen in order to be a function? You may have forgotten from previous lessons, but it must pass the vertical line test. Remember, you can shorten that to VLT whenever you're given a graph. So we're circling the ones that pass the vertical line test. That would be options 1 and options 4. If you have forgotten the vertical line test, let me draw it out for you. Remember, you draw a vertical line, and as long as it hits at more than one place, this one hit at 4, and it can be any of the vertical lines, then it fails the vertical line test. It is not a function. Same thing over here. Okay, it hit twice. fails the vertical line test, not a function. So when you look at the two that we circled, which one is one-to-one? Well, let's think about it. If passing the vertical line test has a vertical line and it shows the x values that repeat, x values cannot repeat, there must be a similar test to seeing if the y values cannot repeat. And let's try a horizontal line test. So if we drew a horizontal line test, just like a vertical line test, it's a terrible horizontal line, but I think you're getting my premise here. It hits more than twice. So option 1 fails the horizontal line test, whereas option 1, it passes the horizontal line test. There's no horizontal line. So of the two graphs, which one is one-to-one? I'm just going to write out option 4, if I can spell correctly, option 4. And my explanation is it passes the horizontal line test. Y values cannot repeat. And that's exactly what the next box talks about. If any given horizontal line passes through the graph of a function at most one time, that means not more than once, then that function is one-to-one. This test works because horizontal lines represent constant y values, and if a horizontal line intersects a graph more than once, an output has been repeated. So as we look at exercise 4, which of the following represents a one-to-one function, make sure it passes both. So just so we're getting, I guess, somewhat good notes here, I'm going to point out that option 1 is not a function. It fails the vertical line test. I'm just going to pray VLT for that. Number 2 is a function because it passes the horizontal line test. But we just learned about the horizontal line test. So that's the one it fails. I'll skip 3 because that's the right answer. What's wrong with option 4? Just like in the previous problem, it fails the horizontal line test. And option 3, the correct answer, passes both. And then we have this other problem. I guess it's our last problem before our notes. We have the distance of a number x lies from the number 5 on a one-dimensional number line is given with this equation. And they want you to show that it is not a one-to-one function. And there's a lot of different options that you could do. There's nothing wrong with guessing and checking, which I think is what they wanted you to do because it says give an example. So what you need to look for is a situation where you have different x values but the same y value. And there's nothing wrong with just guessing and checking and seeing if you could come up with something. So you might want to pause the video and think of something. And what you could do is just guess with like whatever you want, and guess with x. You don't want to guess with y because I think that would make the problem a little bit trickier. And I think most times I do this, students will guess to let x equal 0. Just because 0 is an easy number to work with. Well, if you subtract 5 from 0, you get negative 5. And then the absolute value of that would make it positive 5. Okay, so this is my x, and this is my y. Can you think of another time when the y value would be 5 for a different x value? And again, I'm going to let you think. You could pause the video or you could just continue to let it play because I'm about to answer it. 10. 10 would be that situation because 10 minus 5 would give me 5. And the absolute value of 5 is 5. So do you see how we have the same y value in my two examples with different x values? And that shows, by example, a function that is not one-to-one. One more thing, because, oops, I accidentally just saved that, is if you went to a graphing calculator and you typed in y equals the absolute value of x minus 5, we're not quite ready for that, but when you do, or when we get ready for it, you'll see that it is a V-shaped curve shifted this way. And what you could show by that, it should be a sharp turn right there. It shouldn't have any roundedness to it. It's just a V. It fails the horizontal line test. And you should be ready for your homework at this point on the next page.